Okay, this is a short video segment showing you how to change the ply thickness with minimal effort when using Catia's native FEA solver to determine its deformation and stresses. Okay, so the problem that I'm going to be explaining this thing in the context of a very simple problem. So we have a panel which is 300 millimeter by 100 millimeters, and the thickness of this panel, which is made of a composite material, is 0.33. Actually, I'm going to be using the material properties in the Catia's default database, and for this particular material that I'll show you its properties, the uncued or the cued thickness, which is the ply thickness that's going to participate in the FEA calculation, is 0.33 millimeters. Okay. Later on, I'm going to come back and change this 0.33 the way I want to show you based on unlocking the feature to 0.66 millimeter, and show you that actually the results are going to agree with the original calculation that we did, because the stiffness is going to double. You double the thickness, the stiffness is going to double, and the strain and stress are going to be reduced to half. Okay, so to make things easy, I make only one ply at 0 degrees. Okay, so if we can show whatever we want in the context of this particular problem, you can have arbitrary orientation, you can have multiple layers of plies. Okay, now uh, I'm I'm going to assume that this load that I put at the end, which was 10 Newton per millimeter, is exactly halfway between, somehow applied halfway between the top face of the ply and the bottom face of the ply. So there is no bending, there is no bending deformation. There will ordinarily, if the angle is not 0 or 90, there will also be shear deformation. But for 0 degree or 90 degrees, as I have 0 here, there will be no shear. Okay, it will be just pure extension. Just common sense tell you that it should be pure extension. Okay, just don't forget, if I want to put the load exactly halfway at the midplane, exactly halfway between top and the bottom of the faces of that single ply, I need to say it's symmetric. Okay, now the material database, this is one of the items in the material database. This is a unidirectional, it's over here, it's a unidirectional material. I don't exactly know what this exactly what that material is, but uh, one can check it out. It's either glass or carbon. In all likelihood, either glass or some kind of carbon epoxy. Okay, but the thing is that here, notice that the cued thickness is 0.33 millimeters. So obviously, it's possible for you to create your own material, because you won't be able to change this. This is a catalog item, you cannot change it, but you can make your own material with this information in it, and instead of cued thickness, you put 0.66 later on. And of course, these are the corresponding properties, longitudinal and transverse direction, and things. But I want to show you a different way of doing it. In fact, with some of my older videos, when I did problems that needed to uh, expected me to change the ply, for some reason, I had to do it the way I already explained to you, which is not very good. Okay, so once we do the calculation, it's a very simple, basically extensional problem. We are going to get the force. Force is that nx times the length. This is the force divided by area based on 0.33 millimeter. Okay, and of course the width of 100 millimeter. You're going to get this stress and divided by ex, which is given in the table that I just showed you in Catia. You're going to get the strain of 0.0005, 0.000505. Okay. You can find the extension, the amount of extension based on this is strain, this is the extension. And next, I'm going to make this thickness from 0.33 to 0.66. Repeat the problem. I'll show you how to unlock it, and we'll get there. Okay, when we get there, you'll see. This was done in Catia V5 6 release 2018, and there are some minor changes, minor differences in the interface with some of the older releases. When I say older releases, probably prior to R20, I don't know, 14, 13, whatever. Okay, let's go ahead and do this. I'll put this thing in front of me so that we can refer to it. So let's go ahead first of all and create my part. Let's start with a part file. And my habit is immediately to save this thing. File, save management, save as. I have a folder here. Okay, so on a convenient plane, we are not in generative shape design here, so let me put it back. Generative shape design. Now on a convenient plane, on that horizontal plane, I will sketch something like that. This is 300 millimeters. I've already changed my units. So this is millimeters, and this one is 100 millimeter, 100 millimeters, right there. Okay, and exit, and we fill this thing with a surface right there. This is the fill icon, fill. Or I could have drawn a line and extruded it, either way. And my habit is always to join this thing, because when you join, the plate or the surface will have a direction. I'm going to flip this direction down because when you measure the shell elements, the direction of the normal to the shell element is always opposite to the direction of the surface. And I, I want my normal to the shell to point always up. It's just easier for me to orient myself. You don't have to do that. Okay, now we're going to go to, oh yeah, we can create a rosette here, but I'll do that later because you can create a coordinate system here, there's no problem, and then use it as a rosette later on. Even if you forgot, in the next step, when you go to the composite design, you can create a rosette on the fly. So that's what I'm going to do, okay? So I'm going to click on, composite design. Okay, the first thing you need to do is define the parameters, composite parameters, and I'm going to add a material, and I'm going to go to the default database, Catia default database composite, and I'm going to choose the first one. This is the one that I was showing you. Okay, all right, good. Now, as far as the direction is concerned, I don't have to do anything special because I'm going to be using 0 anyways. Okay, and the rosette, since there is no rosette or anything that are created, you can do it on the fly. Add a rosette, right click, create a system. Now, when you do that, automatically it puts it at the global 0. But of course, you can move it if you want, but this is fine. So I'm going to use this. Notice that it put it there. If you want, you can move it to the left so that you separate it from that. As a matter of fact, let me do that. So let's say that create a point, and I'm going to move this thing to the left so that I can see my rosette better. There, I'm going to put it right there. Okay, and make sure that you uncheck this current system because you want the measurements with respect to the original coordinate system and not with respect to this rosette that I created. All right, let's hide this thing. It looks scary. So fine. That's pretty much it. As I said, direction, we don't need anything special. It's already one of the default ones. Okay, good. Why don't we save this? Okay, so now we're going to create, it's a single ply. I'm going to create a ply group and manually create that ply. So I'm going to say ply group. The surface is right there. The draping direction, I'll make it up. That's entirely up to me. Rosette was automatically picked, and we say OK. Okay, so a plies group has been created here, and I'm going to create my one and only ply that I want. So it's right there. Ply, where do you want to put it? In that ply group. And the boundary is that sketch. It's obvious. Attribute 0 degrees, that material that I selected. Okay, I already put it in my parameters. Good. Now, before I do the rest of the problem, let me hide my material, hide hide my stacking sequence. Oh, not there. Hide it. And hide my sketch. And the reason I do this is later on when I put some restraints, I may inadvertently select the sketch, for example. First of all, it won't let me select the sketch, but sometimes you select a line or a point, and that is not a legitimate selection that transfers into finite element calculation. This is why I always hide my sketch and stacking sequence. Okay, good. Incidentally, if you want, you can look at your stack. Uh, where is this ply exploder? Where did I put it? You see, is this the one? Yeah, exploder right there. And apply group 1, apply 50 times, not 50 times, first of all, 10 times. And then because it's hiding, I can't see it, maybe I should unhide it and then put it back. There we are, okay? These are different ways of doing it. You can show it with a plane like with a plane like that, or with a volume thingy like this, cancel. All right, fine. It's correct. So let me hide my composite properties, hide it. Actually, that doesn't bother me. It's okay. So now we're going to go to advanced meshing tools. And I'm going to mesh this thing with a surface mesher where I have the ability to create nice quad type elements, parabolic quad type elements, okay, and 10 millimeters, so there'll be 30 this way, and no, wait a minute, if this was 30 or 30 this way and 10 in the width direction, and mesh it, or zap it as I call it. There we are. And you can, yeah, okay, so this is done. Exit this. We're done here, so we go to generative structure analysis. This is where you have to apply loads and things of that type. Okay, so first of all, let's look at the mesh. Put the cursor on the nodes and elements, right-click mesh visualization, and change the rendering here to not shaded, so you can see that 10 this way, 30 that way. And to do the rest of the problem, you have to hide the mesh. You cannot put restraints and forces and things like that on the mesh. You have to hide it. Contrary to Abacus and some other answers that you can, this is not a node-driven type of node or element-driven type of a package. Okay, so anyway, deactivate this. Good. So first of all, let's put our loads here. Okay, the loads here. So I'm going to put the not the distributed line force density on this edge in this direction, in the direction of F, in the direction of X. It was 10 newtons per millimeter, which translates into 10,000 newtons per meter. Okay, so that's all right. And then I put the same thing on the other side, except with a negative number. So I put this thing on the other side, the negative number. Okay. Now, in principle, I haven't specified my data yet, my composite data yet. I can do that right now. So let's say now imported composite properties. The support is that surface. I'm going to do it by the ply. The ply is that ply group that I hid it here. Okay, you don't have to bring it into show mode, but you can select it by expanding the tree right there. It's good. And remember, because I said I'm going to place it symmetrically, so this is checked. Now, in principle, if you run this problem, it's going to bomb out because this is a structure which is under a load to the right and under the load to the left, and this can move as a rigid body, still be in static equilibrium. You have to take away that rigid body motion. There are different ways of doing it. One way is to apply the 1, 2, 3 rule. For example, this point does not move in direction 1, 2, 3. This point does not move in the direction 1 and 3. And this point does not move in the direction 3. You do that yourself. Or the easy way out, but be careful because this can get you into trouble sometimes. You think you have done it right, but you got to be careful. That 1, 2, 3 rule can automatically be imposed as long as you know what you're doing with this anchor. Okay, if you look at the earlier videos on composite, the first 10, I don't know, 10, 11, I did the 1, 2, 3 rule, I think, or maybe at least the first 3, 4. You click on it, you don't have to select everything. Basically, it says that if you have a rigid body motion, take it away. All right, I can run this and there won't be any problem. It's going to run, and we're going to check out our results with hand calculations. Okay, done. Now, don't let this thing scare you, because if I say show me the deformation, it feels, if you look at the view from the top, you may get the impression that this is shearing, but it's not shearing. Look, 90-degree angles. See, the 90-degree angles remained at 90 degrees. This is a stretching in that direction, but it's not shearing. Of course, if the angle was not 0, it would shear, but not here. Okay, so how do we check our results? All right, so we can go there to static case solution, right click, generate image. Let's plot our strains, okay? Or how about stresses? Okay, so filter it out with the stresses, and what we want is sigma x. So let's say full component of stress, say okay. But I want, go here, oops. Let's go here, double click on it. I want the component in the direction x, so uh, C11. Okay, now let me see for a second here. Let me change this thing to material shading. Okay, fine. Now, if you put the cursor, look, most of the stuff is 3.03, right? 3.03. As a matter of fact, let me just look at the stress distribution in the middle section. Okay, so the easiest way of doing that is, let me see, let me deactivate this and create a, because what you see here is some kind of an end effect. It's really not end effect, but that has to do with the fact that direction of the, see now, let me let me check something here for you for a second. Let me go there. More, not local, global. Yeah. Okay. The reason that you had that weird figure is because the direction 1 and 2 of these elements close to that end would change, okay? 1 becomes 2, 2 becomes 1. That is why you get that weird, kind of a shape. But if I go to the global direction, so when I say sigma 1, it's in the basically sigma. Look, they're all the same numbers, right? And these numbers clearly agree with right there. It's this number, 3.003, 10 to the 7. That number is the number that you're seeing here, okay? I may have made a mistake here. This may have been, I don't know, this may be 3.03. Oh no, this may be wrong, okay? Check it out, please. You can divide this. I think it should be that, okay? Good. So it agrees with this. Now, let's look at the strain also. So if you look at the strain, again, you go here, right click, generate image. This time filter the strain, and again, component of the strains. Once again, don't show it to me in the local direction. Double click on this. Don't show it to me in the local direction. Show it to me in the global direction. Look, they're all 3 zeros, 505, 3 zeros, what is that? Right here, 3 zeros, 505. Okay? I'm not going to worry about this. So let's say that we now want to repeat the same problem, except that this cued thickness, which the database had 0.33 millimeters, I want to change it double that, 0.66. The problem is this. If you go here to material composite, material used, this, properties, right there. You see, there is a lock here. There is a lock here, right? you can say right click, go, and unlock it. This is one way of doing it. Or you can go here to the apply, which actually comes from up there, and say, put the cursor there, right click, unlock it. Let me go and do it. Let me do it here because this thing that I have here for you, this slide that I have for you, I think it is, let me see for a second. I'm showing it at the ply level. I can do it from here, from ply, or I can do it from the thing all the way on the top. In other words, at the material properties level. So let me do exactly like it appears in the slide. So I go there, right click, go down here, and say unlock, unlock. And then it asks you, are you sure? And you say yes. Notice that if I double click on this, double click on it, I can go change it. Before, if I double clicked on it, this number would be dim. There's a lock here that would, no, that would, because of the lock that you had there, this would be dim. You cannot do that. But here I unlocked it, so I go and say 66. Say okay. Now, it looks like everything is done. By the way, let me check here. See, when I did that, it automatically changed the thing in the material parameters used. It automatically did it. But the problem is that if I go and try to run it, let me go back to the analysis. Let me go back and run it. Remember, the stain was this, 30505. Nothing happens. You see, nothing happens. That's because what you need to do is really redo this import composite property. So first thing I'm going to do, I'm going to deactivate this. You can either delete it and do it again, or double click on it. It says the face has not changed, but the ply has changed. Okay, so I'm going to click on the ply here, and I'm going to select this thing. The first time you select it, it actually, the first time you pick it, it deselects that, and then you pick it again. Either this or the ply group, makes no difference. Okay, now where I run it, I better get half of those strains that I have, half of 0.505, etc. 300505, 30505. Okay, so let's run it. Both the stress and strain are going to be halved, and even the displacement that I didn't bother checking is going to be half too. So let's do that. Activate the strain. That's half of what we had before. Remember, it was 30505 for strain. Deactivate this. Activate the stress. Remember, it was 0.00303, which I had an extra zero in between the two threes, but fixed it. So it is this number. Now, notice that once again, if you go up here, and if you want to keep this thing as 0.606, lock it. Okay. Okay. So let me show you. Remember, this is what I changed. I unlocked it. Now, if you want to keep it at this value, you put the cursor there, right click, and lock it. Okay. So people can't go and fool around with that database because you locked it. But if you want to unlock it, unlock, say okay. The lock goes away, and you can go and change these numbers. Okay. So some of you may have known this, or they may know another way of doing it, which may even be better. But this is something that's not very well documented in the Catia's native FEA solver for composites, and this is why I decided to make this video clip for you. Good luck.